Welcome to this workshop on structural equation modeling, organized in collaboration between Oslo USAR and the Center for Educational Measurement at the University of Oslo. My name is Henrik. I will be moderating this workshop. I'm one of the organizers of Oslo USAR, in addition to doing a PhD at CEMO. The workshop will be given to us by CEMO's professor, Ronny Scherer. Ronny has a wide variety of topics in his research portfolio, but one of them is structural equation modeling. In addition, he teaches the course measurement model at CEMO's master program. I hope you enjoy the workshop and welcome to Ronny.
All right. Right. So, yeah, this is a workshop named A Mild Introduction to Structural Equation Modeling, and we're basically using the R package called lavaan. Now, a couple of things I would like to mention beforehand, before we dive into the topic and dive into some coding. Now, I think we should be rather relaxed about learning structural equation modeling and also lavaan. So lean back a bit, don't start off your R engines already, because I would like to talk first a bit about what this structural equation modeling thing in fact is. For those of you who are already, professionals in the area of structural equation modeling, you could also lean back a bit. Some of it may be a repetition. I may highlight a couple of things every now and then. And I will also simplify a couple of things, given the fact that we are having a quite condensed workshop here. So basically, in the very first place, I would like to introduce SEM. I'd like to ask the question, what is that thing? What can it do for us? And how do we engage in that thing called structural equation modeling? I'd like to also highlight a couple of examples and showcase some applications of it. And then we will directly move into a part where I would like to pull up lavaan and would like to, live code a couple of things. So I've got a specific theory I'm going to introduce you into in a minute, and I would like to test that theory on the basis of a data set. Now, after the introduction of SEM, so basically in the practical part, I would like to, show a bit how to do things in lavaan, but also sneak in every now and then a couple of tasks for you in case you would like to engage in the coding directly on spot. So we hope to make that a bit interactive. Right, let me just see whether I forgot something to mention over here. Yeah, okay, I think I talked about everything. So without any further ado, I think we can get started. Good evening, everyone. So after the advertisement block from Henrik, we will talk about structural equation modeling and its implementation and how it's conducted in lavaan. So I don't know about you, but whenever I talk to people about, for instance, Star Wars, well, some people have very strong opinions. And let alone, if you start off the conversation, do you like Star Wars or Star Trek? Or is it not the same? Oh, how dare you? And I found in the group of people that I'm surrounded with that there are certain camps, some like this, some like the other. And if you're on one camp, you've got quite some prejudice concerning the other one. That's at least what I found with my friends. And I would like to focus the examples for today on prejudice. And I thought, well, what may possibly make them have so much prejudice against the other star thing? Now, I found myself finding at least two possible explanatory variables of this. I think they're not very open. They're not very open to experience, to new things, to, allowing new cultures, new thinking. I also have the hypothesis that on top of the openness, possibly explain their prejudice, it may also be their agreeableness that they may be lacking. And I know you may be thinking this is a very artificial example, and it is, indeed it is. I basically created it here for the sake of this course. But this model, or this hypothesis, this theory I'm having that prejudice can be predicted by both openness and agreeableness, is something that's quite popular in the field of social psychology. And this example will basically guide us through in the lavaan coding. So we'll answer the questions today, the research questions, if you will. First of all, to what extent do those two personality traits, openness and agreeableness, predict prejudice or the variation between people in prejudice? And at the very same time, we'll also, after the question, to what extent might this explanation by those two variables be the same between the two variables? So perhaps openness and agreeableness explain variation and prejudice to different extents. And we're testing this question, or basically testing the hypothesis that they may in fact predict prejudice to the same extent. So that's basically the research program for today's practical sessions. But before that, let us dive into what this structural equation modeling thing that Henrik also mentioned a couple of times, in fact, is. So I'd like to bring up a bit of a background here to explain the main points, I think, behind structural equation modeling before we dive into the actual coding. So when you look up a couple of definitions of structural equation modeling, abbreviated as SEM, you'll find, for example, this one. It's a class of methods, and this part I really like, that seeks to represent hypotheses. So with structural equation modeling, we're basically trying to translate the hypotheses, the theories we're having, into something that we can test, into some model structure that we can basically test against the data. Now, these hypotheses are made basically about means, variances, and also covariances of variables in a data set. And we're trying to translate these hypotheses, or these theories, into parameters, so-called structural parameters, that we can test. And ultimately, what we're doing, to zoom out a tiny bit, is that we are coming in with a theory, we are coming in with a hypothesis, with some kind of a model, and we are translating it into something that we can test and find out whether or not the data would represent that theory and that hypothesis. Another definition highlights two main aspects of SEM, and that's basically, it's a multivariate technique. So we're not only talking about one variable, so it's multiple variables, in fact, that we have hypotheses on. And they also highlight the fact that we are coming in with our theories and we're trying to test even quite complex theories, for example, relationships among many, many variables. So that's, I think, the stage behind structural equation modeling. Now, why bother with this thing? I mean, describing relationships between variables, I mean, you can do many, many different things, networks, or, you know, simple description of profiles, for example, and so forth. But why in particular structural equation modeling as a one feasible technique here? So what's so special about it? And I think there are a couple of reasons. I would like to highlight a couple of them. Now, the first thing is, and that will become important in the practical sessions as well, with SEM, we can represent what we think may be behind the variables in the data set as unobserved, so-called latent variables, or sometimes even called constructs. And we may therefore, for instance, control for measurement error in variables. That will come in a bit later. I will explain that a bit more in greater detail later on. Another advantage of why we could bother with SEM is that SEM allows us to estimate derived effects. So for instance, if we've got the hypothesis that three variables are related in a certain manner, we can not only look at direct effects of one variable on the other, but also indirect effects of one variable on the other via another one. That's quite typical for so-called mediation models. Another specialty about SEM is that those models can be represented, I think, quite nicely visually in so-called path diagrams. And when we draw all those path diagrams, it becomes quite clear to anyone who reads about our model what the bits and pieces of that model are. And that also facilitates some replication. SEM covers a broad range of different models. So for example, you can have hypotheses on a certain model, so how certain variables are related between, let's say, men and women. So a multi-group aspect can be added quite easily in SEM. You may also find yourself in a situation where you're not interested in what, for example, which variables explain students within certain schools, but actually to what extent those variables are related for schools. So you can also change the level of analysis. And that means that SEM can basically be extended to also multi-level models. Or you may be interested in a longitudinal setting where change in certain variables happens over time. And SEM offers quite a bunch of models to describe that change and also its shape. So in this sense, there are loads of different types of models here, and it's quite a flexible framework. And finally, SEM has the advantage to also, or let's put it this way, it can be based not only on the full data set you may hand over to it, but also on summary data. So in case you would like to replicate a paper, and usually authors would report descriptive statistics and correlations among variables, SEM, given this information, so summary data, correlations, and descriptive statistics, allows you to replicate possible findings and possible models in there, because it can handle summary data and is in fact based on variances, covariances, and means, and that's it. All right, so that's, I think, are some of the points that I think make SEM quite special, and there may be many, many, many more.
We have a question. There are other models that are not structural that can include latent constructs like hidden Markov models? What's any main differences?
Okay, so I mean, in this particular scenario, structural basically means that we are hypothesizing some direction in the relationships between variables. So we would, for example, in the example that I pulled up some minutes ago, we would hypothesize that openness and agreeableness, they are the predictors, and there's one outcome variable. And the relationships describing those arrows that I drew here, those are basically representing the structural part of that model. So whenever there's a hypothesis on certain directions in a relationship, that's what we call structural model here. So I think that's to some degree comparable to hidden Markov models, but not exactly identical. It's a bit of a different context, I would say.
If you have any follow-up questions, Andre, you're welcome to ask them. Okay.
Okay, all right, so much for this. Now let's get a bit more practical. A bit more practical in the sense that I would like to show 3 examples of structural equation models from different fields. And I think you may be surprised where this thing can be applied. So I browsed through some key journals such as Science and Nature, not expecting to find anything. Because usually, from my perspective, SEM is heavily applied in psychology and education. I mean, loads of papers in there. Most of the questions in educational effectiveness, for example, we present with those. Now, I was very, very surprised to find quite a number of examples in natural sciences, ecology, and so forth. And I was even more surprised to find that the first structural equation model that had been published was published in biology. So here's another example that I found. Here's an example, the first example that I found. So this has been a paper by Patrick and colleagues, and they've been looking into some ecology measures. So they've been hypothesizing relations among all those variables you see here under what is called Model A. I just let that sink in a bit because there are quite a number of relationships here. And there's been one outcome variable they ultimately wanted to predict. It's called the ACSP. It's the annual community secondary production. It's a sum of annual production of invertebrate population. So some kind of a measurement of population that we find in a certain area. And they hypothesized that this proportion would be predicted by all sorts of climate factors, water temperature, certain flow of water in the course of 30 days, the watershed area as well, precipitation, forest cover, and so forth, latitude as well, air temperature, elevation, and so forth. And those are the relationships that they hypothesized. It was their theory to come up with. Ultimately, they wanted to predict the ASCP values using all these different variables. And you can see that it's not just a regression model where there are a couple of predictor variables predicting ACSP, but those predictors per se and themselves are sometimes predicted by other variables in addition, making, I think, the relations, or the structural relations in that model quite complex. That was my example from biology, or let's say ecology. Got two more. Here's a very old one. This paper has been published in the 70s by Sybil. And you can see that, over time, the type of representation and also the colors have changed a little. Now, in this particular paper, it's a very basic educational paper. The authors wanted to predict occupational attainment. And that's what's called the variable x1. Yeah, that's what they called x1 as the ultimate outcome variable. And they used all sorts of other variables and placed them as predictors or possible other explanatory variables to find out what may predict a student's occupational attainment over time. It's basically been farm boys they've been looking into. And you see there are all sorts of variables in there. They labeled them, I think, from x2 down to x8. And they show quite some complex relations. So some of them predict others, x7, for example, which indicated the socioeconomic status of farm boys. Predicted x5 here, that is the significant others influence. So they also looked a bit of, marriage status here. And they also hypothesized some covariation between variables, for example, x7 and x8, so socioeconomic status and mental ability. Now, without going into detail here, I just want to showcase that this is sort of the theory they came up with. They hypothesized how all these variables are related and how they may explain variation in the ultimate outcome, namely occupational attainment. Now, in that paper, all those variables, x1 down to x8, had been collected. So all these variables, and we'll learn a bit later about what that means, have been called manifest. So they were measured. They were directly in the data set. And my final example from the area of psychology is this. These researchers, Benedek and colleagues, were interested in the question, which executive functions, so very basic cognitive skills of updating your memory, shifting between tasks, and inhibiting, or let's say preventing distractions, would predict the overall cognitive abilities of a sample of students. And they represented those cognitive abilities as what's called here GF, that's fluid intelligence, and also their creativity. So we've got 3 predictive variables in there and 2 outcome variables, and they had the hypothesis that the outcomes are related, and all of the 3 executive functions would predict those 2 outcomes. Now, the difference to the models you've just seen is quite remarkable, I would say, that all the variables they've got in there, so the key variables they were interested in, updating, for example, shifting, inhibition, GF, creativity, are not represented or had not been represented in the dataset. They were not directly measured in the dataset. It's not one score of updating, it's not one score of shifting, not a score of inhibition and so forth. But instead, these authors collected a couple of scores from which they thought they would measure updating, shifting, inhibition, and so forth. So for instance, I'm taking the updating example here, they administered 3 different tasks and tests to students, NBAC1, NBAC2, and NBAC3, without explaining what that is now. And they hypothesized that behind the scores, and particularly their variation and covariation, would be a variable that we cannot directly observe. And we would assume and hypothesize that this represents updating skills. This concept will come up a bit later and all over again in the second part. And to already mention and drop the term here, in this model they represented updating as a so-called latent or unobserved variable, hypothesizing that this represents the construct or the course, the skill behind NBAC1, NBAC2, and NBAC3. Okay, these have been the very brief example I just wanted to highlight, and I think they're already quite complex models here, and also some complex representations of the key concepts and constructs that these authors made hypotheses on. All right, now, social equation modeling. We've just seen, I've just talked about what it is. So a multivariate technique. So we've got multiple variables in the data set, and we are hypothesizing some relationships between them. So it's our theory, our hypothesis we're coming in with. And now we're trying to translate this into something we can measure. But how exactly does that work? This translation part, and how do we end up having those numbers in this model, for example, here? How do we end up with the regression coefficients here, 0.53, 0.29, and ultimately, is this a good model? So in the next part, I would briefly like to talk about the steps of structural equation modeling and highlight those key questions that I've posed. Now, once again, how to do structural equation modeling? Once again, we come in with our hypotheses and theories about the relationships between variables. We translate it into something we can measure. That's the so-called model specification. And then we think about, can we in fact specify, can we in fact test such a model? So is this model identified in terms of, do we have enough information from the data set to in fact estimate such a model and its parameters? Then of course we estimate a model, and then in the very end we evaluate that model given some criteria, and perhaps we may find that some of the bits and pieces in our model may not be aligned very well, so we may re-specify that model again and start all over again. So those are the 4 key steps, I would say, in structural equation modeling. And I would briefly like to go through this, because these are also the very steps, except for the second one, that we will have to implement in lavaan. So the first part, the model specification. Now this is the grammar of a model. So we are coming in with our hypotheses and theories, and we translate them into something we can test. And in order to do this, we would usually mathematically specify a couple of equations. So this one predicts that one, this one is related or co-varies with the other one, and so forth. Today we'll basically have a graphical representation only, not the mathematical one. And we would represent our hypotheses on the relationships among variables using those possible equations. So we represent them by regression coefficients, variances, covariances. You've already seen those unobserved latent variables in there. we may have some hypotheses on how a concept or construct is measured. And we may also have some hypotheses about how they are structurally related. So, for example, which variable predicts which one. In lavaan, there are basically 3 key commands to write down the grammar of this model. So to write down the so-called model specification, to say what is this model actually that we're trying to test. And one key command is the regression command. That's the single tilde. Popped up here an example, y tilde x means that the variable y is predicted by, or you could say regressed on, the predictor variable x. In lavaan, we can also specify and translate our hypotheses into covariances using the so-called double tilde. In this example here, y double tilde x means that the variable y covaries with the variable x. And this will be a bit more important later on in the course. In this workshop, we can define these unobserved variables that are not in the data set, trying to pull together all the variation and covariation of some variables we have in the data set. And we can define those so-called unobserved latent variables using the equals tilde command. So in this example here, eta is just the name I gave, it's an arbitrary name, equals tilde, and then there's a set of variables we've got in our data set, x1, x2, and x3 means we define an unobserved latent variable that we don't have in the data set by a set of variables we have in the data set, and those are x1 down to x3. So those 3 commands I think are the most important to memorize and to also get a grip on later on. Well, once we've got to the grammar of a model, once we've written down what that model is and what a hypothesis in fact is, so the very complex arrows you've seen on the ecology example, the educational example, or the psychological example, once we've gone down to this one, we also have to think about, is this model a meaningful model? So can we meaningfully estimate all the parameters we've just translated our hypotheses to? So is this model essentially identified? Or in other words, it's so-called a feasibility check. That's the question we are after here. Do we have enough information from the data set to estimate all the different parameters in our model? In order to do this, we'd have to compare what is in fact the information we get from the data set. And the key information will be variances, covariances, and means. And then we also have to think about what are the parameters in the model we would like to estimate, we would like to draw inferences on. And those would also be variances, covariances, regression coefficients, sometimes even an intercept. And you will later learn that it can also be some kind of factor loadings, but that comes in later. And then we've got more observed information. Then we've got model parameters, or let's say if we've got at least the same amount observed information and model parameters, we can estimate that model. So the rule generally is we need at least the same amount of observed information than model parameters. Then this model is so-called identified and it's got some degrees of freedom. So say we are in this lucky situation that we've translated our hypothesis into something that we can test. So we specify that model and we know we've got enough information, we've got enough variables in the data set. How do we estimate those parameters? And I think this is a science in itself, and I think I'll only highlight, well, a couple of things here. So how are those model parameters we'd like to draw inferences on, we'd like to use to test our hypotheses estimated? And the key is this. In our data set, we've got observed, well, variances and covariances among all the variables there. So we've got what we call an observed covariance matrix. Now, we're estimating the model parameters, all the regression coefficients and all the numbers on the paths we've just seen, as long or in such a way that we're trying to approximate this observed covariance matrix. Or in other words, we will estimate model parameters so that the covariance matrix we would get from those parameters would be very, very close, or in the best case, identical to the observed covariance matrix in the data set. So we're trying to reduce the discrepancy between observed covariance matrix and the covariance matrix we would get back if we used the parameters in the model. And for this, a couple of estimation procedures have been developed. I think Carl Jodeskog, one of the godfathers of structured equation modeling, he started out with maximum likelihood estimation to reduce this gap and also maximize the likelihood of the data, the probability of the model parameters given the data. There's also the option of using weighted least squares types of estimations to reduce this discrepancy. And there's also Bayesian estimation out there to estimate the model parameters to reduce the difference between the observed and the model implied covariance matrix. So that's, I think, the main story, and I think I shall leave it at that. So once we've got a translation of our hypotheses and theories into something we can test, once we've specified a model, and once we're sure we can in fact estimate the model meaningfully, so we can identify it, and we then estimated a model. Once we've done all that, we should ask the question, is that model a good model? So what are options to evaluate whether or not a model is a good model? And there are also a couple of possibilities out there. And once again, I think this is also a science in itself. But the main reasoning is basically to, in fact, say that a model is good and fits the data very well, if indeed, once again, this discrepancy between the observed covariance matrix in the data and the covariance matrix we would get from the parameters we estimate is very small. Now, over time, a couple of indices have been developed that would help us make a decision on whether or not a model is acceptable or marginally acceptable or hardly acceptable. And those indices are so-called global fit indices. So they look at how your model as a whole would represent the data. So there's a chi-square statistic, for example, that gives you the difference between this observed and model implied covariance matrix. Should be insignificant, because then we have evidence that the two do not really differ. There is a comparative fit index, and some rules suggest that this index should be very close to 1, preferably greater or equal than 0.95. There's the root mean square error of approximation, RMSEA, and some rules of thumb suggest this one should be smaller or equal to 0.08, the very same threshold for what's called a standardized root mean square residual. Now, I won't go into details concerning those fit indices now. I'd like to recommend, for example, the Hoyle book or the Kleiner book on structured equation modeling. And I think after this workshop, you'll also receive the material with all the references to check it out in case you want to. But I would like to say one thing here. Those guidelines, those rules of thumb, I think everyone should take with a bit of a grain of salt, because they've been validated in a very, very limited context. And we sometimes tend to, transfer those guidelines into scenarios in which they may have not been tested that much. So that's why please do take those rules, not as golden rules, but with a bit of grain of salt, and try to use at least 1, 2, perhaps even 3 different indices to say whether or not a model is good. Right, so these are the steps of structured equation modeling. We translate our theories and hypotheses into something we can test. We check out whether we can in fact estimate the parameters in the model meaningfully. And we estimate those parameters, and then we check out whether or not the model is any good. Right, I hope you're still with me, because now we are transitioning into the practical part. I'm sorry, it took a bit longer than anticipated, but it was important to me to at least highlight the key aspects and the key steps in SEM and what it is, because ultimately those steps we will have to take in lavaan. Right, okay. So let us get back to our example, to this, well, straightforward theory, predicting prejudice by openness and agreeableness in people. Asking the two questions, to what extent do those two personality traits explain variation in prejudice? And do they explain variation to the very same extent? In order to address these questions, I found a lovely data set that in fact captured those three different variables. And it's a data set that was created by Berg and colleagues in 2016, or perhaps even earlier. At least they published it in 2016. And they had a couple of variables in there. So let's just have a look at those variables there. 861 data points we have, 861 individuals represent the rows in the data set. And for each of these individuals, we've got 10 composite scores, the ones below, and we've got information on people's gender. Now, there are four variables, the first four: ethnic prejudice, sexism, sexual prejudice against gays and lesbians, prejudice toward mentally people with disabilities. So those are the variables, and the scores, the composite scores, they used to assess prejudice, different forms of prejudice. But those are the four indicators they used to represent prejudice. The other ones, A1 down to A3, are the indicators, some responses to a questionnaire perhaps, of agreeableness. So one of the predictors we're interested in. And O1 down to O3 are the indicators, the manifest observed variables that we've got in our data set representing openness. Unfortunately, we don't have much more information on what these indicators of agreeableness and openness would be. So we can just assume it's been different aspects of it, perhaps different questions that people have been asked. And this is the data set I want us to work on today. You'll find this data set readily stored and made in the R package MPsychoR. And in there, it's the data set Berg. Right, so let's get started with testing a hypothesis on whether or not agreeableness and openness would predict variation in prejudice. And this is the first thing I would like to do. I would like to start with a very simple structural equation model. I mean, some of you may know it under the name multiple linear regression, which is in fact a special case of structural equation modeling, if you will. So I would first of all find some variable that represents prejudice, y, and then predict it by x1 and x2. So predict it by openness that represents x1 and agreeableness that represents x2. To simplify things here, and also because we've got multiple measures of prejudice and multiple measures of openness and agreeableness, I would like to use their sum scores. So I'm using the sum score of all prejudice variables, and similarly for openness and agreeableness, their sum scores. Now, this representation of the regression model is a so-called path diagram. So representing all the variables that are actually in the data set. so that are observed, that are measured, y, x1, and x2 in the rectangle. The variables we cannot measure, so the variables that are derived, unobserved variables, such as a residual EY, those we represent in circles or ellipses. Covariances we represent with a double arrow, so the curved arrow here. And the variances of x1 and the variances of the variance of x2, we also represent as, these double arrows, but, we're basically keeping them on this one variable only, because the covariation, the variation of a variable is the covariation of that variable with itself. And then we've got the regression paths, or the regression structure here, saying that x1 predicts y and x2 predicts y as well. And the regression coefficients I called b1 and b2. Right, so this very first step already means here, I've translated my hypothesis on the prejudice, openness, and agreeable thing into a simple regression model with one outcome variable and two predictors. And I want us now to specify and estimate and evaluate that model in lavaan. Minus, once again, that in the data set we only have those variables and rectangles. Right, in order to do that, I will switch from this PowerPoint presentation to RStudio and engaging in some live coding to show how we can implement this in lavaan. This is a very easy example, and we build it up step by step in a bit. So I'll share RStudio here. I hope you're able to see it. In case you find the font size to be too small, I would like to encourage you to pop a message in the chat, and then I'm trying to sort of increase it. This is also coding material we will share afterwards, but I would also like to encourage you to perhaps even consider coding together with us. So for this example, first of all, we're setting the scene. So I'm using the library lavaan, the package lavaan, for actually, in fact, doing the structural equation modeling. I also use the library semPlot. semPlot as a library that allows us to visualize a structural equation modeling using the path diagram I've just showed you. MPsychoR I'll use to, get in the data set, and I'll use corrplot a bit later throughout the course to, create a correlation plot, as the name suggests. So let's basically load all these packages and access their functions. So I'm going to clean up the output a tiny bit. Here we go. Now, the data set I want us to use is the Berg data set. So let's select that first. So the data set is the one called Berg. Jumps down here already. And let's briefly look at how this data set looks like. Sorry, it jumps down quite inefficiently. Let me just put that up here to avoid jumping up and down too much. Okay, so the dataset Berg, I just took a few function here to pull it up. So this dataset, and it may be a bit too small to you. If it's indeed too small, please check out the slides. Oh, you don't have them, sorry. So let me just say what these variables are, I'm sorry. So the first column is the variable EP, second one SP, then HP, and then DP. So those four first variables are in fact the variables representing prejudice. Then we've got three variables, A1 down to A3, representing agreeableness, some score of it. The next three variables, O1 down to O3, are the variables for openness. And then we've got gender coded as male and female. So I think a very straightforward data set and well prepared by, Berg and colleagues. And Patrick Meyer, who in fact wrote the package. So just for the ease of use, I will attach that data set to avoid using all sorts of, dollar signs and directly access the variable names. Just to check that I've got the correct data set, let's see about the sample size. Do we in fact have those 861 data points in there that we were promised? So let's just check the number of rows as one possible indicator. And we can see we've got 861 rows in there indicating the different persons who responded to the questions. Now remember, the model that I showed you was a basic regression model, and I suggested that we take the mean or create the mean of all those different indicators of prejudice and all those different indicators of agreeableness and all those different indicators of openness to just have it all summarized in one variable. We will later see that that may have not been the best decision. So let's create those scores of the outcome variable y and those two predictor variables x1 and x2. So I'm going to create the mean scores here. Let me call the openness mean score simply open. So I'm going to define a new variable in the Berg dataset as the mean score between 01, 02, and 03. You can also use some mean function if you like to. Should give you the very same outcome. And the very same for agreeableness. I'm going to define this new variable representing agreeableness as the mean between those three variables. Then I'm also going to do the very same thing for prejudice. So let's just call it prejudice. 4 variables, EP, SP, DP, and HP, and I'm basically attaching the mean of those 4 variables. Just going to run that command here. I mean, this is something I do not need to do. I mean, I could have also just picked one of each of those indicators. That would also be a possible, perhaps feasible solution. But I would like to get, let's say, all of the information I've got from those 3 or 4 different indicators of openness, agreeableness, and prejudice. So let's see whether that one worked out. So I'm going to go back to the Berg dataset, and for me it's worked. So there's an overall openness score now, an overall agreement score, agreeableness score, and overall prejudice score. Well, I mean, most of you, I think, are professionals in using R, so my R skills are, well, not as professional as I would love to have them. So I'm feeling a bit like an 11-year-old talking to an adult trying to do his or her text detection. But anyway, you may find an easier way to simply create those new scores and yeah, some more neat functions, I guess. But this is just a very arbitrary way here. So we've got those 3 new scores, and now let us specify, estimate, and evaluate this regression model. Remember the steps in SEM. We translate the hypotheses, so this regression thing, into a model. So we're doing the model specification. So what I do first is I give this whole model that I would like to test the name. So let's call it model 1. I define that as a new object. And now I'm basically using the grammar of lavaan to spell out what that model and the relationships between the variables I'm hypothesizing would look like. So I'm putting all this definition part in the single exclamation marks. Give it a bit more space here. And in there, I can make comments. In there, I can basically write out the grammar that underlie my new hypothesis, or the hypothesis. So let's say we are hypothesizing the structural relations between all these variables. So that means, remember, it's been a regression model. We're using prejudice, so this new variable I've just created, as an outcome variable, and we're predicting it by two predictor variables. So we are using the single tilde to indicate that prediction or this regression. So I'm regressing here the new variable prejudice on the new variables openness and agreeableness. That's, I think, the main part of this model. There are also a couple of more parts here, because those two predictor variables, they have a covariance and they also have variances. So I also tell lavaan, hey, please also estimate for me variances and covariances. So I'm doing that using the double tilde. So the covariance between openness and agreeableness, I write as open, double tilde, and then agreeableness. The variance of openness, I write as openness, double tilde, so covaries with itself, open. I'm doing the very same thing for agreeableness. And these are already all the hypotheses I had on that model. I hypothesized prejudice is an outcome variable. I've got two predictors, openness and agreeableness. All the predictors, so there's two, can covary and they can vary. That's all I just told lavaan here. And that's the grammar of that model. That's the regression model, the linear regression model written out. I'm a friend of also labeling things. So I also prefer to give regression coefficients names, just to find them in the graphical representation or to work with them later on. So I'm going to give the two regression coefficients of openness and agreeableness names. So let's say the regression coefficient for openness should be B1. So I name it B1. And to indicate that this is a name of a coefficient, I write in times. And the very same thing for agreeableness, I'm going to call it B2 times agreeableness, giving it a simple name. And that's it. This is basically the model specification part. So let's just run this command. And now if you have seen that down here, we've got the model 1 defined down there. Clear up things here. All right, now this has not yet been the estimation part. That comes in now. So let's estimate this model here. So here we go. So lavaan offers a couple of different functions, all of which have tiny little differences, particularly in how they start the entire estimation procedure. And I'm going to choose the one that I find to have the least convergence issues in even complex models, and that is called the SEM function. So this whole estimation, I give a name, store everything that happens in the estimation that will come out of it in the name, in the object I call arbitrarily model1.fit. You can call it something else if you'd like to. And then I'm using this SEM function to estimate this structural equation model, or let's say this regression model. Now this SEM function takes a couple of arguments. First of all, sorry, I'm just going to put that up again. First of all, it takes, and we have to hand over the model that we've just specified. So SEM, and we hand over model 1. to it. Then, of course, the function also needs the data set. So the data set is the Berg data set. And then the question is, how are those parameters estimated? And by default, lavaan uses the maximum likelihood estimation. I'm just going to write that out again. It's a default. We don't have to. But I'm going to tell lavaan again, please, as an estimator, use maximum likelihood estimation. And I will also make another argument, put in another argument here. And it's also sometimes a matter of taste, sometimes also a matter of your research question. In this case, I'm only interested in relationships between variables. I don't want the means to be estimated there. I don't want the intercept of prejudice to be in there. So I'll turn off the mean structure of the model, and there is the argument mean structure in lavaan, and I'll turn that off. So we are no longer having, in a regression context, the intercept of prejudice in there. And that's also, for now, a very arbitrary decision. And throughout all the models that you'll see today, there won't be a mean structure in there. Because, and this is a very bad word joke, because this mean structure to us today is not meaningful, or doesn't mean something. I know this is very mean. Okay, let's continue. So we handed over the model, we handed over the data set, told lavaan which estimator to use, and we turned off the estimation of the mean structure. So I'm going to run this here. And then I would like to pull up the results of this model estimation. So for this, lavaan has the summary function. And in this summary function, I will, of course, specify what needs to be summarized. So it's basically the model 1 fit. And I think this is very lovely, lavaan offers so many different options to give us in the output directly. For instance, we are in a regression context, so I would want to know how much of the variation in prejudice is explained by the two other variables. So I want some measure of variance explanation, so some R squared. Well, there is an option, an argument in lavaan R squared equals true, set it to true, and then it will give us directly this variance explanation. I also want standardized results. So not only the B coefficients in this regression model, but also the beta coefficients where all sorts of variables in there are set standardized or set transformed. So I'm going to tell the summary function, please give me the standardized solution here. And I would also want lavaan to give me an account, does this model really fit? So I can also call directly for fit measures in the summary function, and I set them to true. So once again, we hand over the model we've just estimated with all its different parameters in there. We ask for the variance explanation R squared, ask for standardized results as well, and fit measures. So let's see how that model looks like. So I'm going to scroll up a bit because there's loads of stuff we will get here. And I will also, take a bit more time for this example to also show you the different functions and the different possibilities lavaan has to give you as an output. In the other examples, we're going to go through things a bit faster, or a bit more briefly, let's put it this way. So lavaan summarized to me the number of iterations it's done. It's also summarized to me the whole estimation procedure, the optimization methods behind it. And it will also summarize and give me an account of the sample size that we've got. Free parameters are those parameters in the model that are in fact not constrained. They are freely estimated in the model. And then it will give me all sorts of stuff. For example, and I won't go through everything here, but it gives me, for instance, a model test user model, a test statistic. It's 0, degrees of freedom 0. Now, that is the chi-square statistic I've talked about a couple of minutes ago. This is the statistic indicating to me, is there a difference between the observed covariance matrix and the covariance matrix we would get from the model parameters, and it's 0. And also no degrees of freedom. Hang on, degrees of freedom, that guy has just talked about identification and that we would need more pieces of information data set than model parameters. Well, in fact, this suggests here, degrees of freedom of 0 suggests that we have exactly as many pieces of information, so variances and covariances in the data set as we have parameters in the model. So they match. So this model is exactly identified. So we can meaningfully estimate parameters. Okay, I will just scroll further down, skipping a couple of things here. So here, for example, the indices I also pulled up some minutes ago, the so-called CFI, it's 1.0. If that's completely perfect, I told you it should be close to 1. Well, that's 1. That's very close to 1, I think. We get some information on how the maximum likelihood estimation procedure worked out, or let's say the resultant log likelihood. We also get the information criteria, AIC, BIC, some sample size adjusted BIC, to possibly compare this model against another one. We've got the RMSEA, the one I showed you, it's 0, it's perfect. SIMR is also 0, perfect. Now, I mean, for those indices I told you about in the first part, we find this model is just perfect. Well, it is perfect because it's exactly identified. We've got exactly enough pieces of information as we have parameters in the model. So those indices, RMSEA, SIMR and stuff, they're not really meaningful here because this model is exactly identified. More importantly, I scroll further down, we find all the regression coefficients. So, okay, yeah, hope you see that here. It broke down things into 2 lines. I apologize about that. Sorry about that. So B1 is this regression coefficient connecting openness and prejudice. We've got its estimate, its standard error, a Z statistic, testing it against 0, the corresponding p-value of that very test, and we've got the fully standardized, the so-called beta coefficient you would find from normal regression. The very same thing we've got for agreeableness. You could think, I mean, just seeing the numbers, B1 and B2, so minus 0.61 and minus 0.32, that there may be a difference between those two, so they may not be equal. Later on, we'll test that. Now, this particular model would also suggest to us that the higher people are on openness for a certain value of their agreeableness, so the more open they are, basically, the less prejudice they would show on the scales we've just seen. So on the average of those 4 measures. Okay. And then if we scroll further down, we also get covariances between the 2 predictors here, openness and agreeableness. If we standardize things, we get the correlation, it's 0.25. So openness and agreeableness, as we've set up those 2 variables in the data set, are positively correlated. And we also have evidence that the covariation behind it deviates from 0. And then finally, lavaan gives us the variances that we asked for, the variance of openness, the variance of agreeableness, and, well, the so-called residual variance of prejudice. So the variance we cannot explain in the outcome variable. And finally, the actual information I was longing for, the extent to which those 2 variables explain variation in prejudice, and we get an R-squared of 0.277, so roughly 27.7% of the outcome variable's variation is explained by both agreeableness and openness. So I think my theory perfectly works, doesn't it? I mean, we do have some evidence that we do explain almost 28% of variation in the outcome using those 2 personality traits. Now, before we probably would like to engage you a tiny bit, and then also I think before we take a short break, I would say, I'd like to show you a couple of more functions in lavaan. So hang on, just going to scroll up a bit. What would I like to pull up? Yeah. When I talked about, model estimation, also model evaluation, I told you that lavaan, or the whole structured equation modeling thing, compares the observed covariance matrix with the one that comes from the model parameters we've just estimated. So basically, the difference between the two could give us some so-called residuals. And the residuals I can pull up using lavaan's ready-made function that is called resid. So with the resid function, I get the residuals indicating the discrepancy between those two covariance matrices. So the resid function needs from us the name of the model we've estimated. And then we've got a plethora of different options, different residuals. So raw residuals, for example, or standardized residuals. So let's pull out the raw residuals as an example here. So I'm telling lavaan, please give me the residuals that are raw residuals. So the direct difference between observed and model implied covariance matrix. So if I run that command here, find a brief summary which type it's been, and these are the residuals between those two covariance matrices. And you can see in all entries of this covariance matrix, we've got 0 residuals because we're perfectly replicating the observed covariance matrix. This model is perfectly identified, we would say. If I in fact want to know what is this covariance matrix that comes from the model parameters, I would directly see it in front of me. lavaan has this very neat function to give it as an output. So to see the model implied covariance matrix, you can use the fitted function in lavaan, and I only hand over to lavaan the model that I estimated. So using this function, I would see here the very covariance matrix that comes from the data set. If you compare that to the original covariance matrix, we haven't done that so far, then you will see there's hardly any discrepancy between the two. And that happens with models where you've got exactly enough information in from the data set as you have model parameters to be estimated. I think 2.5 more things, 3 things I would like to highlight. Then we're becoming a bit more practical. If I want to see all the different model parameters directly under each other with, for instance, confidence intervals, so regression coefficients and their confidence intervals, lavaan allows me to pull them up using the parameter estimates function. So parameter estimates function over here. What I basically do is I tell lavaan, this is the model I've just estimated. Give me all parameter estimates. So if I run that, I'll see all the different parameter estimates. So I see here the regression coefficient connecting openness and prejudice. I labeled it B1. Its estimate, we've already seen that already, but this is a bit of a different summary here. Its standard error, set statistic, p-value, and then also the confidence intervals. And those are the walled confidence intervals. So confidence intervals that assume that there is some normality in the data set. And then I get the second regression coefficient, all the different variances and covariances are called for, and also the residual variation, the variation we do not explain. In prejudice, so basically, yeah, that residual variation. Okay, that's sometimes quite neat if you want to translate and hand over those parameter estimates directly to a table and want to have it in a paper, or in a table that you would like to show somewhere. Sometimes easier to pull out those parameter estimates using this function rather than the summary function. And then finally, if you remember, I had a second question with that model. I was not only interested in to what extent do those two variables explain variance in the outcome variable, but I also had the hypothesis or the question that they may explain variation to the very same extent, or I could rephrase that they are related to prejudice to the very same extent. So I may test the hypothesis that the regression coefficient B1 is the very same as the regression coefficient B2. And there are many, many options to do this in lavaan. I would like to show you one of them. And this is performing a so-called walled test. We test directly the equality of those two different regression parameters. And lavaan has a function called LAV test walled. And what I do here is I hand over the model that I've just estimated, and I tell lavaan, please test the following. So I'm going to give it a so-called constraint. And then I specify that what I would like to test in there. So I'd like to test that B1 is the very same as B2. And then it would perform a so-called walled test, give me a test statistic, and so-called omega statistic for those of you who are into the matter. And then will also give me a p-value to indicate whether or not I've got evidence backing or not backing this hypothesis. So let us run this here, and there we get the walled statistic. It's an omega statistic here, degrees of freedom belonging to it. We get a p-value that is very, very, very small, roughly 2.5 times 10 to the power of -5. So we do have evidence, in fact, that those two regression coefficient, and now here's the interpretation thing, that those two regression coefficients are not the same. The reasoning behind this test is basically we are specifying in the background a model where we assume them to be equal, comparing that model to the model where they're not equal, and the discrepancy is basically indicated by the statistic over here. And if we find a significant result, we've got evidence that the model where we constrain things fits worse. So this is one possible way of hypothesis testing, and a bit later I think I will show you a second one as well. Right.
Nice time to take a short break.
Yes, exactly. That was in fact the moment to also for me to say, well, let's take a short break and then we'll come back. So Henry.
So welcome back, and just the floor is yours again, Ronny. But this question that popped up during the break from Ervan. Could you emphasize on perfectly identified model? Don't we have many more respondents than parameters?
Okay, right. Thanks for this question. Now, this identification thing and perfectly identified model only takes into consideration the number of information we've got from the data set, independent of the sample size and the parameters we have. So remember, we had this regression model mainly comprising 3 different variables. So what we've got available from the data set are 3 variances, well, the variance of y, x1 and x2. And we've got 3 covariances, so all the covariance between the different combinations of those variables. So we've got 6 pieces of information in there that does not take into consideration the sample size. And as model parameters, we had 2 regression coefficients, B1, B2. We had the variance of x1, the variance of x2, the covariance between x1 and x2, and we had a variance of the residual, so the variance of the leftovers, basically, of the outcome variable. That makes 6 parameters in the model. 6 pieces of information, variances, covariances, and 6 parameters in the model, and that means we've got exactly enough information as we need. Okay, great. Thanks for the feedback. All right, wow, that was quite a stretch, wasn't it? I mean, quite some input. And now let's just see a couple of different types of models we can add and specify in lavaan. So I'm bringing up the presentation again. Once again, we will share this presentation with you. You'll find also some additional material in there. You'll also find some additional code in the files that we will, I think, then send out later on. So I'm coming back here, and we are here. Right, now remember, we had this hypothesis with the prejudice and the openness and agreeableness as 2 possible predictors. And I also mentioned that we skipped the mean structure in that particular model. So that was not really of interest to us. Means are usually, that as a side note, represented in a path diagram through a triangle with a 1 in there. So it's just another, let's say, predictor, the identity predictor, basically. Okay, that's only as a side note here. Now, what if my hypothesis, what if I tweaked my hypothesis to something like this? What if I had the hypothesis that, in fact, it's not openness and agreeableness side by side as 2 predictors that may covary, predict y, but what if I had the hypothesis that agreeableness, represented by x, predicts y directly, so the prejudice variable, but also indirectly through another variable, a so-called mediating variable m, and that's in our case openness. What if there are some more structural paths in the data there? What if this was my hypothesis? What if I tested this? So extending basically the regression model to not only 1 equation, but 2 equations for 2 outcome variables, because now suddenly not only y is predicted and has some causes, but also m, openness in our case. Now, I want you to think during the next 3 minutes, I'm going to go back to this in a bit. I want you to think for the next 3 minutes, how would I have to change the model specification we've just seen, you know, the thing with all the tildes, to test this model instead of the other one. So please do take 3 minutes, and perhaps you may even try out in R how to specify it there. So once again, try to think about how would I have to modify the code from the regression part into something that tests this. So we're going to take roughly now 2.5 more minutes to let you think or test out. While you're thinking, I think I'm going to make a couple of comments here. This is a very typical model tested in experimental research, especially in psychology, where you would assume that there's a mediating variable between 2 other variables. So not only direct paths, direct connections between variables, but also indirect connections through other variables. Right, I think you've seen that model now, so I will now slowly turn to R and get back to a possible specification. Okay, so right, so now I'm slowly presenting how we could possibly specify this. You may want to check with your ideas here. So this has been the specification we've seen in lavaan so far. It's a regression model, basically, where prejudice is the only outcome variable. And now to modify that, to test the other model, we basically add a next line defining that also openness can be predicted by agreeableness. So scrolling further down, I call this model, by the way, model 2 now. So I called this model 2 here. So now it's no longer only that prejudice is predicted by openness and agreeableness, but also openness predicted by, and there we use the tilde for this, agreeableness. And now only agreeableness is the only variable that does not have a cause. So only the variance of agreeableness is the additional parameter we're estimating here. There's no longer the variation of openness or the covariation between openness and agreeableness. Okay, all right. I will add one more detail here. Now, remember what I briefly elaborated on at the beginning. Why is SEM so special? Why bother? And one of the reasons has been that we can derive certain effects from those models. Now, in this particular model where X and Y are directly but also indirectly related through another variable openness, I can also pull out this very indirect effect. And this very indirect effect is basically the product of the two regression coefficients that represent this indirect effect. So I can define here this indirect effect I would like to have. And this indirect effect I would like to see and like to have is the product of B1 and B3. So that's the new parameter I can tell lavaan to estimate. And this generally new parameters are defined in lavaan as, you've got dots here and you've got the equal sign over here. Okay, so it uses B1 and B3, multiplies it together, and then tests it against 0 using, what's in literature called the so-called Sobel test, the Z test. Okay, so I'm going to run this code here, so this specification, and then I'll basically estimate this model. I prepared things a bit in the break to not bore you out too much. So once again, I hand over this new model called model 2 here, the data set, turn off the mean structure and use maximum likelihood estimation. So let's see what we get. So I'm using the summary function here as well to pull out the different parameters. It's just a copy and paste thing from the regression model. I only changed the name of the model. So let's scroll up here. Once again, we will find on top that this model is also perfectly identified. So looking at the fit statistics, we won't see much. Okay, so that's why I'm directly going to the model parameters. And once again, I get B1 and B2. So B1 is now the relationship between X and Y. So the direct relationship between prejudice, the relationship between X and M in the model that we've seen in the slides. The direct relationship between agreeableness and prejudice is represented by B2. We've got B3 now, because now suddenly agreeableness is also a predictor of openness. And we find that the two are related positively. We also have evidence that this new relation we've just added significantly deviates from 0. When I scroll further down, we also see the different variance components. So the variance, the only actual variance of the variable that does not have a coarse agreeableness, so the X variable, and the variances of the residuals, so the leftovers, because we can't perfectly explain prejudice and openness. So these are residual variances here indicated with a dot first. And I also get the information that we, in total, again, explain roughly 28% of variance and prejudice, but also 6% of variance and openness can be explained by agreeableness. And finally, if I scroll further down, I get this very indirect effect. So the size, the magnitude of this mechanism connecting X and Y through this new variable M, so-called mediating or indirect effect. And I see it's negative, it's 0.15 roughly. And I've got evidence that it deviates from 0. So in fact, I have some evidence that there is an indirect pathway from agreeableness to prejudice via openness. It's not a perfect proof, but it's some evidence. As a side note, now testing those new defined parameters against 0 is also based on some assumptions in the model where you say, there's some normality in the data set. Now, the thing is that all these tests, particularly of the indirect effect, so B1 times B3 here, it's been controversially discussed, and some do no longer believe in those p-values that are presented here by the so-called Sobel test or the respective confidence intervals. So that's why the literature now suggests using something alternative that does not rely on normality assumptions, such as a bootstrapping. And we won't do that right now because it takes quite a bit to run through. Lavaan has a very, very neat functionality as part of the SEM function to do for you the bootstrapping of the standard errors and ultimately confidence intervals. So you don't have to rely on some normality assumption that may be behind this new defined indirect effect. Okay, right. So much for this. And I would like to show you finally how to visualize this model. And this is a product that our lovely teaching assistant and PhD candidate at CEMO created for us in the course, in the measurement model course. Thank you, Yal. Using the function in the, using the function in the semPlot package. Now this function is the function called semParse, and in semParse it will give you basically some settings how to visualize the very model you've just specified. Now it's probably going to look a bit ugly now, or let's say a bit small, so I'm trying my best to increase the size a tiny bit. If you do it on your own, you may see it much bigger and much larger. So if I run this ready-made code here, I think in the first place you see we hand over the model to this function. Then there are some specifications concerning its layout. And we'll also see standardized model results there. So if I run this semParse model here, directly translates the model and the values into a path diagram. And red arrows in this scenario are indicating negative relationships between variables, and the gray ones, the positive ones. We'll see some residual variation of openness 0.94 and prejudice 0.72. And then we have the regression coefficients in there as well. That's sometimes a very neat, check on whether or not you've, run the right model. Okay, all right. So I'm going to delete that now. There will be a couple of more representations later on. Okay. So I'm going back to the slides, and I'd like to move on a bit because those two types of models, so both the regression model and also the mediation model, where we hypothesize an indirect relationship of two variables through another one, I think you can address also with simple regression. to a certain extent. But there are a set of models that you cannot directly address with simple regression. And let me elaborate on those. Those are basically models that contain what is called latent, so unobserved variables that are not directly in the data set. Now here's the example. Remember, agreeableness, openness, and prejudice. In the very beginning, I created the sum scores, or let's say the average scores, as a matter of fact, the average scores of all those different indicators, all those different measures of agreeableness, openness, and prejudice, because I didn't want to make a decision for either one. So I just wanted to say, well, I'm taking all of them instead of just one. Now, when we create, for instance, the average of all the different agreeableness indicators, A1 down to A3, we're sort of summarizing all the variation and covariation among those three indicators in one variable. Now, what we're also doing is we're allowing measurement error in the actual regression model that we've just run. So we're allowing to have this new composite average variable to introduce bias to, for instance, the regression parameters. Bias because this new variable has unreliability. Of course, we're not perfectly measuring the truth. We're not perfectly measuring the true score of agreeableness. Now, you may say, oh dear, Ronny, that's bad, or that can be bad. What to do about it? I mean, I don't want to choose one indicator of agreeableness. I don't want to create a mean score. So what can I do to approximate as best as possible a true score of agreeableness? Well, one possible way to do this is to use all of the different indicators of agreeableness in the data set. So I'm using here in this particular model we will look at now in the next 10 minutes, I think. I'm using here the indicators A1, A2, and A3 at the very same time. And I know from the study that all of those indicators, to some degree, or to perhaps even different degrees, indicate agreeableness. They somehow measured aspects of it. So I can hypothesize, this is again my theory, I can hypothesize that behind, plainly speaking, behind all those three indicators is something unobserved that I don't have directly in the data set, a so-called latent or unobserved variable. And I called it AG for agreeableness. Or in other words, I'm trying to take out all the variation, I'm trying to summarize all the variation and covariation among those three scores in the data set A1, A2, and A3, capture this in a new variable that's not in my data set, it's an artificially defined variable, and I call that variable agreeableness. I hypothesize that this is something measuring agreeableness. So I'm summarizing information from those three different indicators. And in addition to this, I'm also separating the measurement error from a possible true score in all those three different variables. Because once I've hypothesized this latent, unobserved thing AG, I use it as a predictor of the variables in the data set. And that means I also have some residuals that may indicate measurement error or unreliability. That's also a very neat way, and psychologists, I think, can sing a song of it, if that phrase exists in English. In German it does. That when you've got a battery of different tests and you think those different batteries are in fact measuring the very same thing, instead of pulling it all together to a mean score, I'd like to summarize all the information from those scores in one variable. And one way to represent them quite well is the latent variable concept. Okay, so coming back to our example, I'm now moving to representing those three variables I was interested in my theory as latent unobserved variables now measured by the variables that are in the data set. So how is that done in lavaan? So I'm going back to here. I prepared a couple of things. And I will call that model model 3. And it will be a so-called measurement model. So I'm trying to measure that unobserved concept of agreeableness using 3 observed measured variables. And for those of you who are into the matter, this is confirmatory factor analysis. So how do I measure, how do I represent those variables and set up those latent unobserved variables? So let us begin with agreeableness. And I will call this new variable that's not in the data set AG. And I'll define it using the equals tilde command. I think a couple of minutes ago, almost hours ago, I told you about this. And I hypothesize that agreeableness is measured by 3 observed variables in the data set, namely A1, A2, and A3. In the very same way, you can identify and define the openness construct. We're now using the term construct for something that's not directly observable. It's the indicators O1, O2, and O3. And the very same for prejudice. So for prejudice, I had the 4 indicators, in fact, 4 different scores, different variables, EP, SP, I've got HP and DP. Now notice that we're no longer using the mean scores we've created in the first place. So those are now the so-called measurement models. And then of course I would want to allow that all these different newly defined variables have variation, and they can also covary. So we are adding some covariance structure here. So I'm saying that agreeableness can covary with openness, but also with prejudice. And openness can covary with prejudice. And all of those 3 variables also have a variation, and there are different ways now to write that out. I think I'm taking the long version here. So agreeableness has a variance, openness has a variance, and prejudice has got a variance. And this is basically only a definition of those unobserved variables. And we're now running a model that contains those 3 different unobserved variables and their covariance and variances. We're not yet testing the hypothesis of, to what extent does this and that predict prejudice. That comes in a couple of minutes. All right, so the equals tilde thing defines unobserved variables in the data set. And I know there's so many different aspects to talk about here and so many different specialties and defaults that lavaan also has, but I just want to give you a very brief overview of how things work here. So you may want to check out the default settings also in lavaan. So I'm creating this new object here. And then, similar to the regression example, I'm using the SEM function with the very same settings except for the different model name to estimate that model. That was quick. Now let's see how the summary goes and what's in fact in that object. So I'm using, once again, the summary function. Okay. So let me scroll up to the very top here. Once again, we've got a summary of what we've just done. 861 observations, we haven't lost anyone. And now we suddenly have this chi-square statistic 186.6, 32 degrees of freedom. So this model is no longer exactly identified. We've got more information from the data set, from those 10 variables, then we've got parameters in the model that we're estimating. And the difference is basically 32. We do see the statistic here. It's significant, indicating that, well, there is some deviation between the observed and the model implied covariance matrix. So we're not perfectly replicating what we've got in the data. So it's not a very perfect model. And that's also indicated by the CFI should be very close to 1. Remember, a couple of minutes ago, it's been 1.00, 0.96, still acceptable. Scroll further down, RMSEA should be below 0.08. We are still in that range here. And SRMR should also be below 0.08 roughly. And we're very well in that range. So that's, I would say, an acceptable but not perfect model that we've got to describe this new construct, these new latent variables, these unobserved things we call agreeableness, openness, and prejudice. So then we get all sorts of parameters in there. So first of all, lavaan tells us, hey, you've just defined latent variables, and here they are, AG, OP, and PR. And those are indicated by all those measured variables, all those observed variables in the data set. And these estimates here are now the regression coefficients connecting them. Given that this is a special definition of some new variable, we no longer call them regression coefficients, but factor loadings. So we get all those values over here. We have evidence that they deviate from 0. If we standardize everything, then we see for OP, so sorry, for agreeableness, those guys over here in the SED all part column, they're fairly high. So in fact, those 3 different indicators of agreeableness, they, well, reliably measure agreeableness, or something we called agreeableness. The very same for openness, fairly high, almost homogeneous regression coefficients or factor loadings. And then we've got prejudice here, and I think here the numbers are a bit mixed. We've got one that's quite low, and the highest one about 0.75. So those 4 indicators of prejudice may not perfectly reliably represent prejudice. So there's at least one possible outlier, let's put it this way. Outlier also in the sense that this one may be correlated to all other prejudice indicators quite low. And then finally, we get all the covariances between those variables. So if we look at the standardized option directly, it's the correlation. So we see that agreeableness and openness positively covary, and agreeableness and prejudice, but also agreeableness and openness, they have negative covariation. I think that was well in line with what we've seen previously from the regression example where we used the mean scores. Okay, and finally an account of all the different variances. I'm just going to scroll further down here, and also the extent to which these new latent variables explain variation in the indicators. So for instance, in A1, this first indicator of agreeableness, the latent variable that we defined explains roughly 71.6% of a variation. And I think the lowest one is this indicator HP of prejudice, explaining only 12%, only 12% of the variation in there is explained by the latent variable we called prejudice. Right, finally, and almost as a last point on this model here, I'm going to check whether we specified, in fact, the correct model. So trying to visualize it here using the semPaths function. And again, 3 latent variables, that's correct. We've got that, they all covary, lovely. and they all have indicators, and you see the factor loadings directly on the paths. And those are the standardized results here. I asked for them using the what equals STD.
There's a question from the chat, Ronny.
Okay.
Let's see, the first one is, based on your experience, what is the acceptable value of an error of a factor loading?
If I understood correctly, it was the error of a factor loading?
Yes.
Okay, well, I don't want to generalize now certain numbers here. If it's large, there may be something wrong with the model, whatever large means, in fact. I think for a latent variable that's defined by a set of different variables you've got in your data set, so manifest variables, I would always compare the standard errors of all sorts of factor loadings of that very latent variable. And if one pops out to have very large standard errors, I would check it out. And I would try to see what happens if I exclude that particular variable. Do I still have a model with fairly high factor loadings? And perhaps that may be an option to reduce the model and drop one of the indicators. But I don't have a very strong suggestion here in terms of a number. I'm sorry.
Is there any follow-up question, Irena? And then there's a different question regarding the categorical data. What if your data is categorical, like a questionnaire where a subject responds on a scale from 0 to 3? Do you tell lavaan what type of data you got?
Yeah, well, now this particular scenario where you've got 4 different response options from 0 to 3 is sometimes considered in literature as a bit of a borderline scenario. When the distributions of the items are roughly normal, you may not tell lavaan, hey, here are categorical data. You may treat them normally, but you may correct from possible deviations from normality. And lavaan offers you to switch the estimator to robust maximum likelihood estimation, for example, so that you can accommodate possible deviations from normality. If, however, you got some skewed data and some of the categories are not really populated with people responding to them, I would definitely use an estimation procedure in lavaan that treats them categorically. So you would tell lavaan in the SEM function, hey, here are ordinal, or let's generalize it, categorical data, and you would switch the estimator. So you would change from estimator equals ML to some categorical estimator, such as weighted least squares estimation. In the very last slide, at the very end of this workshop, I pulled up a couple of options there. But in a nutshell, I think it really depends on how the item distributions look like. Are they fairly normal? Or do we have major departures from normality? But lavaan allows for categorical data treatment. Yes, it does.
Thanks.
Okay, thanks for the questions. Appreciate that. Oh, sorry. Okay, that was a short muting thing here. Right. So this is basically only to check that we can represent PROP and AG as latent variables. And now in the next step, I would like to plug them into our regression model, because now I no longer want to represent those 3 different variables, the 3 different concepts, as their average score, but as latent unobserved variables, getting all the information in from the different indicators from the data set. Before that, some researcher has found, and I won't go into detail now where this information comes from, some research found that in fact, the model could perhaps be improved by adding a covariance between the indicators A1 and A3. Now, this researcher may have looked into the actual indicators, the questions that had been asked on agreeableness, and they may have found that beyond the fact that they may measure agreeableness, as represented by the variable AG, the wordings may be also quite similar, or the formulation or the terms they use may be quite similar. So there may be some connection, aka some covariation between those 2 indicators, A1 and A3, beyond agreeableness as a concept that's behind it. And so these researchers hypothesized, hey, perhaps there is also a covariation between A1 and A3. In the next 2 minutes, I want you to think about how do you include from the code that I've just showed you, and I will pull it up in a minute again, how could you include this possible covariation in the specification of the model? So what needs to change to add this? Just leave it for 1 minute, then I slowly get to lavaan to show it. So I'm slowly moving into the RStudio environment. And by the way, this is the one before the last model I will show you in lavaan. So we're almost there. So this has been the specification of the original model, and now how to tweak it, how to account for the fact that A1 and A3 may possibly measure something in addition to agreeableness. All right. I'm slowly going down there. And I think most of you have already seen that. Okay, I'm just going to accommodate it to the fact that we've differently. So I think most of you have already, gotten what's happening here. We are adding this very covariation. Covariations are added, covariants are added by using the double tilde. So we're adding to the model we've just specified the covariation between A1 and A3. That's the difference. So let's see what happens before we get to the very final model. So I'm running this one. I only added A1 tilde tilde A3. Now let's estimate this model. Call it model 3B. You may call it something different. And then again, the same settings of the summary function and also the SEM function. I haven't changed anything here. So we run this, and then I'm scrolling up, and let's see what happens. Remember, the chi-square statistics of the other model without that tiny little covariation was about 180 or 186 or something. Now it's been reduced. So we're getting closer to the observed covariance matrix. That's a good sign. Remember, the CFI of the other model was about 0.96 something. That's increased as well, 0.98 roughly. So actually representing the data better than previously. The RMSCA was a bit about 0.70, 75 or something. It's down to 57, 0.057. Also improved.
This regard, there's a question from the chat. Is not correlating residuals kind of cheating from Ina?
I think this really depends on the reasoning behind introducing those residual correlations, or covariations. If you're running such a model that I've just shown you, and you're using some indices to say, oh, well, I could improve the model if I only added this or that and this and that, only for the sake of improving the model, you may consider this to be cheating or tweaking to make a model fit. But here, as I explained to you, there was a substantive reasoning behind this, namely that the formulation of the items beyond that those items or questions have measured agreeableness use the same wordings or had some kind of a similar formulation. In this case, I would say, and don't take that as a law here, but in this case, I would say you've got some theoretical ground to add them, and I would not consider this to be irresponsible, but theory-driven.
Thanks. And there's also another question. Let's see. Why the loadings of A1, O4, and EP were fixed as 1 in the slides?
Yeah, so that's a very arbitrary choice, I must say. So I simply chose to define the scale and to define that latent variable, that the first factor loading is fixed to 1. That's also needed to, if you consider, that those latent variables and their measurement themselves to sort of, define that variable. There are also other options to sort of set the scale or define this latent variable. By default, the first indicator you hand over to lavaan in defining a latent variable, in our case, for AG it's been A1, for OP it's been O1, for PR it's been EP, will be fixed to 1 automatically. That has to do with the scale setting and the definition of the latent variable. That's sort of needed to meaningfully create those variables. As I said, there are also other options here. I didn't talk about them here.
Thanks.
Okay, wonderful. Lovely to hear your voice, Henrik. It's so lovely to hear, some some noise at a certain point, because you basically can't hear anything. That's an interesting feeling, I think. Okay, so we've seen from the fit statistic, I think, that adding this residual covariance improved some fit indices, and if I scroll to the parameter estimates, this should also pop up in the outcome variable. So we've got what we've already seen previously, the definition of the latent variables and the respective regression coefficients or path factor loadings. That was almost yeah, okay, no recording, I can't say that. Right, and you've got the covariances between the latent variables and also the covariance between those two residuals, A1 and A3 here. So it's got an unstandardized value of 0.066, and if we standardize it to correlation, it's fairly high with 0.56. The question is, did we in fact, or did we really improve the fit of the model to the data after including this residual correlation or covariance, to be more precise? Well, there are different ways to sort of get information and evidence about this. One very neat way, I would say, is using the model comparison ANOVA function. In the ANOVA function, I would hand over to that function the model without the residual covariance and the model with the residual covariance. And let's see what happens. It happens this. It summarizes to us the degrees of freedom. It also summarizes to us the information criteria of both models. And then it performs a difference test between those two chi-square statistics, 118.26 versus 186.62. So there's a difference value there. Both models only have one parameter difference, so the degrees of freedom would be 1. And we find in the last part here, in the last column here, that the respective p-value is smaller than 2.2 times 10 to the power of minus 16. So essentially, we're reducing significantly the chi-square statistic. So we're getting significantly closer to the observed covariance matrix. So we're significantly improving the model fit. For those of you who prefer information criteria, you'll also see that for AIC and BIC, they are consistently lower for the model with that residual covariation than they are for the model without them. Also pointing to the fact that, in fact, we're improving something when adding this residual covariation.
A couple of more questions here.
Mm-hmm.
First one from Alexandra. A more general question. For the logical sequence of testing a certain hypothesis, would not one start with checking the measurement models and only afterwards testing the structural path models?
I agree, yes. And I'm so sorry to not have mentioned that in the beginning when we moved into this area of latent variables. That's in fact what we're doing right now. So in this particular model here, and also the previous one, so 3 and 3b, we're in fact only establishing the measurement models, so those latent variables, before we then later add them to test our hypotheses. Yes, so I would agree. That's the strategy.
There's another question regarding syntax. I'm not sure if I can represent this. It's from Frederick. I can't really represent this accurately right speaking, so it might be better
Okay.
to look at it.
Okay. Okay, I can see it now. So it is when specifying the covariance structure, you are writing AG double tilde OP plus PR. Is there any reason for this? Is it equal to writing the two statements? It is in fact equal to writing the two statements. So the question has basically been, I'm summarizing that briefly here. Can you write that out in two command lines that equal to writing AG double tilde PR and leaving the first one only with OP? Yes, it is. Yes, just a simplified version. I mean, you can see that AG has covariation with OP, with PR as well, but also with itself. So I can also reduce those three different command lines by saying AG covaries with OP, PR, and itself. That's an alternative way of formulating it, but you can write them out. Yes.
And the last question for now. Why do we set mean structure to false? How do I understand mean structure? It's from Xizhong Wu.
Right. Now, in my hypothesis, in my theory, I didn't hypothesize anything on means here. So I didn't, for example, compare the mean of prejudice or the mean of all the other variables between groups of male and female participants. And the only hypotheses that I've had were only concerned with relationships between variables. So only the variances and covariances, to be more precise, the covariance among those variables were of my interest. So that's why I skipped the mean structure. That's usually not something I would recommend. I mean, you can carry over the mean structure in all models that we've just done. It will basically give you some more means, sometimes also called intercepts, if they are means of variables that are predicted by something. But in my case, I didn't see any reason to include it. There was no, let's say, statistical reason for this. It was only a substantive reason that I did not have any hypothesis on the mean structure, so I just skipped them. But you can include them, and I think if you have hypotheses on group differences, for example, in latent variables or the variables themselves that are measured in the data set, please include them. Yes.
Thanks.
Okay, then wonderful. Thank you, Henrik. So now this, as Alexandra, I think, in the chat commented, only led up to my testing of hypothesis that I'm trying to do now. So this was only to set the stage of the latent variables and to define these no longer as means of those variables, but as unobserved variables. So say this is our measurement model. Say this is how we represent agreeableness, openness, and prejudice. So now we can sort of put these pieces together and say, using this representation of the variables and the constructs, what is the variance explained in prejudice by agreeableness and openness. So we're going back to the regression example and now representing the variables as latent. And it looks like this. So we are having those two predictor variables. Now they're no longer the means between A3 and A1 down to A3 and O1 down to A3, but we're using those latent variables we've just defined. And we're using those two, we allow for their covariation and their variation as we do in the regression model, and then predict prejudice, which is now also a latent variable. Now this time, mind us, we've separated as best as we could possible measurement error in the variables in the data set from a possible true score. So the possible true score, if you will, of agreeableness, openness, and prejudice is represented in this latent unobserved variable. And this is the model we're finally testing as an alternative to the regression model in the very beginning. And then I only have 50 more slides. I'm joking. Right, so let's see. And let's also make us aware that we've now combined the measurement part, the definition of those unobserved variables, with hypotheses on the structure between those variables. And we've got all the tools together, how this is basically done and how we can do this in lavaan. And that's why I'm basically sharing the code instead of walking through every single detail. So I'm scrolling a bit further down. And here, oh, I forgot a couple of things. Ah, how dare I? I think we may have to code a bit here. So in this model specification, I now have the three latent variables as we had previously. The residual covariance I put in for theoretical reasons. And now I basically only add the regression part. So I now say, as we did in the regression model in the very beginning called model 1, we now say prejudice is regressed on or predicted by, if you will, openness. And that's now the variable OP, no longer the variable we called open. It's OP now, a latent variable, plus agreeableness, and that's now AG. Once again, I like that better. Depends on your preference here. I like to label those regression coefficients. I'll call them B1 and B2. Again. Mind us, this is in fact almost the very same, well, let's say similar model to test our hypotheses. But there's a key difference here now. We now do not represent all variables as means of other variables, but as an unobserved variable, trying to tear apart the measurement error, trying to control for measurement error. Those of you who know about latent variables, this is a very rough simplification. Please do forgive me. So I define that model here and then estimate it again with the very same settings here. That was rather quick. And then I'll finally get to the summary. Before we get to the summary, let me check the model first and let me visualize it once again. So I'm or as we did for the other models, so I'm visualizing that here using the semPaths function. And this is how it looks like, just to check everything. So prejudice, latent variable, measured by 4 indicators, that's correct. We've got agreeableness, openness, latent variables, predicting prejudice. They can covary, and then we've got the measurement models, so the definition of the latent variables for agreeableness and openness. And also this residual covariation that improved the model fit quite a bit. So that seems correct in terms of the setup.
We have a new question. What about variance and covariance?
Which kind of covariance and variance are we talking about now? I'm so sorry to ask.
They were not specified in the model?
Well, I mean, if you mean variance and covariance, particularly the variances of the residuals of A1, A2, and A3, so the very things we don't explain by this newly defined variable, they're implicitly there, yes. They're just not directly shown, particularly for A2, because they're so small. So those tiny little arrows you may or may not see in the graphical representation, for example, the one at 01, it's got this value 0.32. Perhaps I can zoom that a tiny bit. You may see that a bit better here. So this tiny little value down here at 0.32, that is the variance of the residual of the leftovers basically in 01.
Any chance you could scroll up to the model specification? I assume that's...
Yes, I will. So basically here, and they are automatically estimated, those residual variations, that we do not need to ask for them. We could ask for them. So we could ask for them, for example, in the using 01 varies with itself. That would be the residual variation, the residual variance of 01. We could do that. lavaan gives them to us automatically. I'm just trying to keep the code a bit short and brief. That's why I did not put them in explicitly.
Thanks.
Okay, wonderful.
So, I have a stupid question, actually. You maybe said this earlier, but the dashed lines, what do they indicate?
The dashed lines over here. Okay, that depends a bit on the type of path or path diagram you specified. In this particular path diagram, the dashed lines would indicate the lines where values are fixed to a certain initial value. So for example, in agreeableness, as I told you, the very first factor loading, the first regression coefficient connecting A1 and agreeableness was fixed to 1. That's indicated by the dashed line. The very same for O1, the very same for EP.
Thanks.
Okay. Right, and this is probably the very last output you will see from my side today. It's the summary of all model parameters. So I just ran the summary function here to bring together all the evidence of this model. And let's scroll further up. We see it's got the very same chi-square statistic as our modified measurement model. We didn't really add some new parameters in there. We basically used the ones that we've got, or the number of parameters that we've got. CFI is identical to the measurement model we've just seen, RMSCA and SRMR as well. What's more important, I think, is the structural parameters. So here again, latent variables are defined. I'm going to scroll further down to the actual regression coefficients, and here they are. B1 and B2, the very ones we are interested in. So both are negative. The unstandardized values roughly around minus 0.6. The standardized ones, so the betas, minus 0.444 and minus 0.39. Now, I don't know whether you remember this, but initially when we created the mean scores and used them as predictors, we had quite different regression coefficients. I think one was about minus 0.22, another one was roughly 0.4 something. So the difference between them was quite big. And we also had evidence, remember when we tested this using this Walt test function, that they are in fact different. But here it seems as if they are quite comparable. Namely, roughly in unstandardized fashion, close to minus 0.6. So let me test whether or not they are in fact the same. So I'm using again this test Walt function, handing over the new model, and testing the constraint, or testing the hypothesis, are these two regression coefficients the same? Remember initially in the regression model we found, yes, they are. P-value was indicating a statistical difference between the two. Now let's see what happens here. So if I run this test Walt function, this is the statistics gets me. And now suddenly the p-value would indicate, well, there's no evidence saying that they are different. And that's, I think, a completely different conclusion we would have now concerning that question we had initially. So we would, in the regression model, just pulling together the means of scores, basically infer that two regression coefficients, relationships between those variables, predictive relationships to the outcome variable, are not the same. And here we say they are the same. And that's, I think, a drastic difference in the inferences. And that's a bit of an exclamation mark here that I would like to make. Should be very careful with simply using sum scores or average scores. There are certain conditions under which they are appropriate and not. So for example, if all factor loadings of the indicators, as we had in the definition of latent variables, are quite high and also homogeneous, it may be worthwhile considering sum scores or average scores. But here, remember, in prejudice, they varied quite a lot. One was 0.35, the other one was 0.75 or something. So representing prejudice by simply creating a mean score and average score may not be the best choice. So in this example here, there's quite a drastic difference between different ways to represent the variables or the constructs in the model that we have.
So we have a couple of more questions now.
Okay.
One is from Frederick regarding quality of life, so to speak. You said that lavaan gives you the variance automatically. Does this mean that I don't have to bother with modeling them explicitly as a general rule?
Not necessarily. So it will give you certain variances explicitly. So for instance, in the measurement model part, so have a look at this slide here for OP, it will automatically give you the residual variances of O1, O2, O3. However, it will not give you automatically the covariance between the latent variables AG and OP.
Okay.
It will, right, it will, however, give you automatically, because you say there is an outcome variable and a couple of predictors, it will give you automatically the residual variance of PR. So residual variances in a measurement model will be given automatically, that's for sure. But I mean, you better specify them to be sure that they're actually there.
Thanks. And another question. Why is the loading of A2 on AG so high, 1.0? How should we interpret this?
Well, so the variance that we can explain in this particular manifest variable, in this variable we've got on the dataset A2, by this unobserved, latent, wobbly kind of variable we've defined is quite high. So we could also say that yeah, what's a better interpretation here? Let me just think to put that simply in a bit of better words. It's there's a very strong connection and a very, yeah, you know, there's a whole story behind this latent variance. That's why I'm just trying to find a good and easy way to put it in words. Basically, a strong representation of that particular manifest variable by the latent variable. So we represent very well what that latent variable captures using this particular variable A2.
Then I take it that Eros's question, would A2 be a very good or pure measure of the latent variable? Then the answer is yes.
That could indeed be. We could have chosen A2 as a possible consequence. Yeah, that could be an option, yes. Of course, you have to test out whether the model fits and perhaps also compare it to a model where you've got all indicators, but that could be a possible way to reduce this model and not use all of them. Yeah, thank you. Oh, by the way, I can see a typo in the slides. I do apologize here. The residual covariation was supposed to be between A1 and A3, not A1 and A2. Okay, so that was basically what I would like to present. I've got one more aspect I would like to highlight, or let's say 1.5 more aspects I would like to highlight. And this is basically the flexibility of lavaan and also structural equation modeling. In the slides that we will share, and also the code we will share, you will find that a multi-group structure can easily be added to the models. So for example, if you're not only interested in, for a given sample, how does openness, agreeableness, or some variables predict some other variable for the whole sample, but you may be interested in, is that prediction perhaps different between males and females, or between certain areas in a landscape and other areas in a landscape? You can easily add a multi-group structure to it. And there is a group option with the SEM function that comes along with it. The only thing is, let me just show that here. If I was to compare this model between male and female participants, I would have to make sure, or if I would like to see that B1 and B2 may be different between male and female participants, I would have to make sure that all other parameters in the model, they are highlighted in green here, are in fact comparable. Because if B1 and B2 may differ between male and female participants, that could also be due to the fact that all other parameters may vary between those two groups. So I have to make sure all other parameters, all other relevant parameters, or some set of parameters are invariant, so comparable or equal enough, plainly speaking. Okay. A final comment, and then I think I'm done. And wow, I expected to end at 7. I do apologize. Now that was all, I think, a model that's, or an example, I think that worked out quite well. But what if things in real life do not look as good as we've just seen? So 3 issues, 3 what ifs I'd like to put on the way here. So what if the data are not normally distributed? Somebody made a comment on categorical data. That could be the case. Or if it's count data that are on the data set, what if they're not? Because maximum likelihood estimation as a default relies on assumptions of normality. What if we deviate from that? What if that just doesn't work out? Well, 3 possible solutions lavaan offers. lavaan offers you an asymptotic distribution and estimation. It will also offer you to perform maximum likelihood and be a bit more generous with the standard errors and test statistics by accounting for the fact that you're deviating from normality. And it offers you the option to bootstrap all sorts of standard errors and ultimately confidence intervals. So you could, for example, for an estimator based on asymptotic distribution, use some weighted least squares estimators that are readily available in lavaan, be it WLS or other options. There's also a Bayesian version of lavaan called lavaan, which allows you for setting some priors in a Bayesian context. And all sorts of robust standard errors are available using standard error functions or other types of estimators, basically. Bootstrapping I also put up here. You can bootstrap standard errors or test statistics if normality doesn't play out. 2 more issues may pop up. Data may be missing. You may have holes in the data set, and lavaan offers 3 options, whereby the 3rd one is a bit of a collaboration with other packages as well. To deal with them, lavaan offers you a full information maximum likelihood procedure to deal with them. It offers you also a 2-stage approach, when the first step, from the data, you create a mean vector and a covariance matrix, and then use this to perform SEM. Or there's also the option of imputing, filling in those holes in the data set using multiple imputation. And here are some specifications lavaan offers. So FIML, full information maximum likelihood, it offers you a 2-stage procedure, and with some multiple imputation package mice and the run mice function, for example, in other package SEM tools, it can provide you with the estimates that come from multiple imputation. So it can deal with multiple imputation as well. And finally, what if data are dependent? What if you don't have the participants nicely and independently sampled, but you sampled perhaps schools first and then you sampled students in a school and they responded to all the questions? What if there's some hierarchy in the data set, this example being students nested in schools? Well, lavaan has been extended to multi-level structural equation modeling. And with this option, you can tell lavaan, hey, there's a hierarchical structure in the data set. Please do take it into account. And it will basically take all the variance and covariance components at the different levels as in multi-level modeling into account. And finally, there's also a package lavaan.survey, which allows you to define a survey design. So to tell lavaan, hey, there are students nested in classrooms or schools, and hey, there are even weights in the data set, or there are other specialties coming from a complex large-scale data set. So in this sense, I think lavaan can deal with some of the key issues. There are, of course, a couple of limitations, and the author, Ivis Rosil, is doing, I think, a very good job in updating things, documenting things. So basically, stay tuned what will happen with the package and which other extensions it will give you. Right, and I think I'm done now. And I hope that you got hopefully some usable information on how to deal with structural equation modeling and how to perform structural equation modeling in lavaan. I hope that you got a bit of a glimpse of what it can do for you, and also of the set of different types of models. So having only observed variables in there that are in the data set, but also having variables in there that may be not observed from the data. Right, and I hope this was a bit of a glimpse of how lavaan works and how the steps of structural equation modeling can be implemented. With this, I would like to thank you, and I think getting the word back to Henrik.
Thanks. Then it's my turn to thank you. Let's see, can you hear me?
Oh, yes, yes, yeah. I can absolutely hear you.
Okay,
yeah,
fantastic.
I just muted myself,
yeah.
Sorry.
No, and then we have one more question from the chat, and I was wondering if we can go for 6 more minutes and open for if there's any questions that other people have. That would be nice to have. So if we could start off with the first question from Erwan. Would ANOVA, Model 1 fit and Model 4 fit be a good way to evaluate whether the whole SEM process was a good idea or not?
Okay, now the thing is that the Model 1 contained the means of those variables we've created, so the mean of A1, A2, and A3. So we defined some new variables in there. 3 variables were basically in that model. And in Model 4, we had a structural equation model basically without those means. So in fact, the variables that are contained in those 2 models are completely different. So that's why the chi-square difference test that the ANOVA function offers us, I would not use to say, or to use as an argument, yes or no, the structural equation modeling thing worked out. I think it's the overall fit that you will consider in Model 4 that will tell you, did it work out or did it not?
If there's another question from Stefan. You've experienced comparing M+ to lavaan for intermediate advanced users. Any thoughts?
This is almost a religious question. I'm sorry, do I need to take a stand? Now, I think
you should, and you should argue for R, because it's a USR event and we are arguing for open science.
Well, there are Raoul is clapping, right. Now, there are R packages out that can operate M+. Does that count? Now, I think in certain scenarios, and don't kill me for that, for certain scenarios, I think M+ is much more feasible than the R package lavaan, particularly when you've got very large scale and complex survey data sets. Some of the specialties of large-scale survey data sets I think more efficiently handled in M+. But at the very same time, it's sometimes a bit cumbersome to extract the information, the parameters, the outcomes from MPlus. And that's why you can use an R package called MPlus automation to operate MPlus using R. Slowly but steadily, I think lavaan is getting closer to what MPlus does, and its flexibility has increased over the years a lot. So for the very basic structural equation modeling without major complex survey designs, I would recommend lavaan. For complex survey designs generally, I think I would, check out MPlus as well, or at least consider it.
Nice. If there's not any other questions, I think this is a good time to thank Ronny. Thank you for giving a fantastic lecture. I'll work on getting this recording. We'll look through it before we publish it to make sure it's presentable, and then we'll post it on the Meetup site, and it will also be provided links through different channels that you might have heard from us from. So
Wonderful.
Thank you for coming, and yeah, here in Norway, the sun is out, maybe for an hour or so more. So if you're in Norway or in Oslo, please join for a beer or go outside, enjoy the weather.